vede?
Sigur că da.
Ok, pe o să schimb pe engleză, că prezentarea e în engleză. Sau ați dori în română? Ok, o să continui în engleză atunci. Can you hear me?
Da, vă auzim.
Okay, so my presentation is about a model able to detect the anomalies in the production data. So as the motivation, well, in our days, the automated machines are widely used for the production of different items, let's say like milling machines. And also these machines generate a lot of data, obviously. And the proper execution of these machines is also important. Obviously, it affects the business cost and so on. So in this idea, it's important to detect anomalies and to prevent the unpleasant events. So let's say as a problem description, starting with the unlabeled dataset D, we need to find the anomalous instances. I mean the anomalous data. Obviously, we have some challenges, like the employed method must be effective, I mean to detect the proper anomalies. Also, because the machines generates a lot of data, the model must to be able to handle the data volume. And also, we have a problem related to the anomaly definition. Okay, now for the existing approaches, there exist some supervised classification solutions, but usually we don't have too much labeled data. So keep in mind, this is an unsupervised problem. Also, there exist clustering and unsupervised methods, but again, they have some issues like high memory usage in the case of DBScan, let's say, and also deep learning models. But as we know, they need a lot of resources like computational. Okay, and the proposed method consists of two stages, labeling stage and the training stage, and we will see every stage. For the artificial labeling stage, as I mentioned, we start with a data set with no labels. So we could put some artificial, some synthetic labels on the data. And the idea starts from the fact that we do not know what is an anomaly in general. It's just something that behaves different from the others. And in statistical terms, this is like a value with a low occurrence probability. So in this way, we can estimate the probability distribution function, let's say with the histogram approach, as you've seen in this image, and then to look for the values with low probabilities. So for each feature of the dataset, we estimate the probability distribution using the histogram, and then we look for the values with low probabilities because they are not so common, so they could be anomalies. Now we have like a definition for each feature, and then we could define the anomaly at the instance level. So a record from the dataset is an anomaly if it contains at least k anomalous values. And also we will retain the indices for the anomalous values. And basically this is the artificial labeling stage. Then for the training stage, we have the frequencies of the anomalous values. And then we will generate the subsets of features using a sliding window approach, as you can see in this picture. So let's say the first subset will contain features from 0 to 3, from 1 to 4, and so on. And in this way, we generate a lot of subsets of features, and we select the best subsets using some score values computed obviously using these frequencies. Now we have some estimators and need to train them. So basically for each subset of features, for each window, we take a sample G from the labeled dataset, and G must to contain a certain percentage of anomalous values. This is important for later. And then we have this sample, we compute the centroid value, and then compute the distances between the centroid value and between each instance from the sample. Okay, uh, and of course we obtain some distances values, and for them we compute the percentiles. Okay, and now we have a prediction model, and if we want to make a prediction to test if an instance is an anomaly or not, the prediction function is parameterized with a percentile rank, and basically each estimator will compute the distance between his centroid and the new instance A. And if the distance is greater than the percentile, then the estimator label the instance A as anomaly. And then the model uses a majority vote to decide the final label. Now for the experiment part, I have some energy consumption data from a hydroforming press. Basically, hydroforming uses the liquids to shape pieces in the metals, if you know. So the data set contains 161,000 records with 24 features. 90% of the data is for training and 10% for testing. And also the parameter p prime is 0.02. And also I don't have ground truth labels. Remember, it is an unsupervised problem. And in this way, to validate my results, I use other anomaly detection models, isolation forest and one class SVM. And the logic is that maybe if my model say, I mean predict for an input data, it says it is an anomaly, maybe this doesn't mean too much, okay? But in this way, if other specific models, I mean solutions from the same problem say the same, I mean conclude the same thing, uh, is a high confidence that in reality the input data, the given input data is really an anomaly. And because this matching logic is related to the intersection of the sets, because yeah, each model make the prediction and we check the values for the matching. Uh, the performance metrics are the Jacquard and Dice indexes. Okay, further, this is the name of the proposed model. I will refer it further, okay? And these are just the outcomes predicted by each model, now without the intersection, but keep in mind that, as you can see, the number of anomalies is lower than the number of normal instances, okay? And now we have Jacquard and Dice scores for the instances classified as normal, so not anomalies, and they are close to the one, so it's like almost a perfect prediction. Uh, then we have the the results for the instances classified as anomalies. And again, we can see some height results, but in this case, you can see how important is the percentile value. And it is because this relation, so the link between the optimal percentile and the p prime, remember p prime was 0.02, So yeah, the best results are obtained from the 98 percentile, especially when I intersect the results of my method with one class SVM. As you can see, it's closer to the one of 95. Okay, and as conclusions, well, the proposed methods detect the proper anomalies. Again, I checked with other models to intersect the results. The optimum percentile rank is related with P prime parameter to how many anomalies are used to train the model. And also this parameterized prediction component uh, allow the model to be, let's say, more flexible, to control how strictly to be related to anomalies. And for the feature work, for the selection of estimators, instead of using just score values, like with sliding window, the model could use some heuristic strategies. And also for the computation of the centroids, instead of using just a simple average, so the classic average, to use some weighted average, again, based on the probability distribution and histogram. And that's it. Thank you for the attention. And if somebody has some questions, please. Can you hear me?
Yes, we can hear you. So thank you for your presentation. If my colleagues has okay, I would like to ask you, do you see further development of this project?
Yes, obviously, I have some future directions, and yeah, the methods use both statistical and machine learning elements, so it has potential, obviously. It's like a new approach, a new prediction strategy, let's say.
What programming language do you use?
I use Python. It is the mainly language for the data science and machine learning. And actually let's say the isolation forest and one class SVM are from the Skylearn, if you know the module is a popular one. Scikit-learn, actually.
And how did you conduct the experiments? How were you?
Also, so a teacher provided me some hydroforming data from a project from Arad. And yeah, after
So you got the data set from your teacher?
can you repeat, please?
So you received the data set, no?
Oh, yes, and like
Okay.
a problem
And
to detect
that
the
data set, do you have what characteristic, what fields they contain? It contain?
well, it is actually a time series data,
Okay.
and because the hydroforming press produce the same piece, I mean, it receive a pattern of item and produce the same piece. In the time series data, you will see like a pattern, like a periodic pattern of values. And
So you don't have to show us how the data receive it looks like.
I think I have uh, maybe just a picture, I guess.
Okay.
Okay, can I show you all?
Yes, yes.
Okay, just a second to check something. Uh, I think I have the picture here. So
Okay.
okay, so this is so basically these are the values from the energy consumption.
This is a chart of the values now.
Yes, and
Okay.
as you can see, it's like a periodic behavior because again, the press perform the same operation again and again and again to produce the same item. And I extracted the cycles, I mean the periodic pattern, and on these cycles, a cycle have a size of 24. So there are the features, the attributes.
Okay, thank you, Dacian. We will go next to another representation.